So here we're going to take a look at one of Pauling's rules referred to as the coordination principle. And it is based on this idea of radius ratios. So what are radius ratios? It is a way of thinking about the packing of atoms when atoms are not the same size. So in another video, we'll talk about so-called closest packing and CCP and HCP structures. And I will leave the details to that other video, but you can think of it this way. If we have a bunch of tennis balls, how could we efficiently pack them in a box? And there are certain and different ways of doing that, and some are a little more efficient than others. But the tennis balls here are all the same size. What would happen if we want to mix different size objects, things that are not the same radius? So if we have atoms that are not the same size, and that's usually the case for, let's say, cations and anions, right? The radius of a cation is usually, not always, but usually less than the radius of an anion. If you have a very large cation like uranium, then that might not be the case. But for most common elements in geologically common materials, the cation will usually be smaller than the anion. The electrons have been stripped off here, the anion is gaining electrons, and so for ionically bonded compounds, then we're going to have this relationship typically. So let's take a look at this very nice diagram here from Dexter Perkins' online mineralogy textbook. He has a very small cation here, and it's so small that it can only fit 3 anions around it. So we would say that its coordination number is 3. That's where we get this so-called coordination principle. That coordination number, I'll just fit it in here. So the coordination number is often just abbreviated as C.N. And it is also often shown as a Roman numeral. So we could put a Roman numeral above an element to indicate its coordination number. So in this case, it would be 3. But if we have a slightly larger cation, then it has more room to fit anions around it if we take anions of the same size. So in this case, the coordination number would be 6 in 3 dimensions, taking this geometry here. We'd be able to fit 6 anions around that central cation. So its coordination number then would be 6. And then over here, we have an even larger cation for a fixed anion size, and we get a coordination number of 8. Right? Let's take a look at this in the way it is usually formulated as a ratio of RA over RX, and then we will compare coordination numbers. So what is RA over RX? RA is anti-intuitively the radius of a cation, not the anion. And the Rx then is the radius of the anion. So why do we do this? Well, it's not 100% clear. Partly it's because we talk about things like so-called AX compounds, and that would be something like sodium chloride, or we can have an AX2, which would be something like fluorite, CaF2. But there are exceptions to that rule. We have XO2 compounds like cassiterate, which is SNO2. Now it's the X that is the cation. Don't let that stuff bother you. The bottom line is we're going to take the ratio of a small thing over a large thing. And if that ratio is less than 0.155, so if the cation is small compared to the anion, then we're only going to be able to fit 2 anions about it. So that cation will be bonded to simply 2 anions and no more. And if that ratio is greater than 0.155, but let's say it is less than 0.225, let's erase that, 0.225, then we'd get a coordination number of 3. And you don't have to memorize these. You can always look these numbers up in a textbook or probably even more quickly on Google. For 4-fold coordination, we'd start at 225, which was the upper limit over here, and we'd go up to 0.414. A little dyslexic here, so that's a 414. Then for 6-fold, it would be 0.414 to 0.732. 8-fold, 0.732 to 1, and then 12-fold is when they are equal in size, and then we move on to HCP and CCP type closed pack structures. Let's take an example of how we do this. So let's say the radius of sodium is equal to 1.02 angstroms, and the radius of chlorine is equal to 1.81 angstroms. So this is our RA, this is our Rx over here, and then the ratio would be equal to about 0.56. And if you refer back to that previous chart, that should equate to a sodium atom that would be in 6-fold coordination. So we could write sodium, and then in Roman numerals here, we write the number 6. Sometimes it's also indicated as a 6 in Arabic numerals and then in square brackets. So that would be the coordination number. There is a little bit of circularity here. Now, in terms of the radius of sodium, we might have different choices depending on what kind of coordination state it is in. So we use this to get the coordination number here, but sometimes we need the coordination number to actually figure out the actual radius. So sometimes we have to just put in a range of numbers, especially when we just have unknown compounds and we're not sure how they're going to bond. But even still, sometimes we get a pretty good guide. So if we look up radii for the element cesium, we get numbers like 1.67 and 1.74 and 1.81, depending on what kind of coordination state it's in. But if we want to take cesium and bond it to, let's say, chlorine, where chlorine is, let's say, 1.81, only one radius is given in some tables, then we would get ratios of 0.922 using this fellow, 0.96 using 1.74, and then a radius of 1.0. And all of those fit in with the idea of 8-fold coordinated cesium. And that would be the case where you would have, let's say, a cube with chlorine atoms at the center. And then we could have a central cesium atom here that is now bonded to 1, 2, 3, 4, 5, 6, 7. There's a chlorine in the back that I forgot to draw, and 8. That would be our 8-fold coordination number for cesium. So sometimes even when there's uncertainty here, depending on the coordination number where the analysis for radius is being obtained, we might still converge on a useful answer that might help us predict the kind of structure. Very powerful thing, radius ratios. Just to kind of recap or summarize its importance, the periodic chart does not tell us how things will be coordinated with one another. We can predict that these elements over here might form ionic bonds with these fellows over here. Radius ratios are a way of starting to add some geometry for us to be able to discern the structure of things if we know the relative sizes. It's a little bit circular, but there are some clever ways to try to get at these ratios and then make some simple calculations. It's also why we call these Pauling's rules, not Pauling's laws.